All right, so I'm sure you all got my email since nobody started panicking about the deadline of the lab. So basically the way I want you to do is I want you to make an attempt at your presentation. I know that 2 of the groups still haven't had their semi-wiki posts done. That's fine. It looks like it's going to be, the next one's going to be on Thursday, and then the next one will be next Tuesday. So that'll be perfect. You'll have had some opportunities for a couple people to go on there and post. So focus on that. Class next Tuesday is canceled. Then Thursday will be finished. Thursday we'll be finishing up. Next Thursday we'll finish up section 9. Next Tuesday, when class is canceled, that's when the lab 2 is going to be due, and then next Tuesday will be when lab 3 is going to be due. I cannot give any more extensions. I don't want this spilling over into your finals. So this is pretty much it. This is as late as I can go. Here's the important point about the labs. The lab should at most take you 4 to 5 hours, at most, meaning accounting for doing all the steps and troubleshooting when you get crazy errors. As you guys are finding out, CAD tools can throw you weird errors that you're like, I don't even know why this is doing this. The key thing is, what I want to see is I want to see that you made the honest attempt to do it, and I want to see that you made an attempt to troubleshoot. So in your challenges section, so let's say you lay out your NAND gate like you're doing in lab 2 right now, and you get, I'm going to use yours as an example. Let's say you get 20 errors and they're all in the NMOS section. So you know you've properly designed the PMOS section, right? And you get 20 errors in the electric VLSI tool. It actually has the rules. So let's say you go through, you say, okay, well I got this error and this rule is this, and it's in the layout, it's in your TGOs. So I looked at it, it appeared fine, I can't figure it out, I tried moving things around, and it didn't work. Show me your attempts, show me what you've actually attempted to do to solve it. If you do that, that means you've shown me that you've made the honest attempt. It shows me that you understand the underlying CMOS, and it shows me that you understand troubleshooting. And this shouldn't be taking, I understand that, with the snow, I came from Florida, so it's been a long time since I've done with this. That with the snow, a lot of your other classes, they're trying to smush everything in at the last minute. So I don't want this interfering with your performance in your other courses. So just make sure you take 4 to 5 hours, make sure you document all your troubleshooting steps and make an honest attempt at every step. The portions of the labs are separated enough so that way if you get stuck on one part, it shouldn't get you too stuck on subsequent parts. For example, getting stuck on the NAND gate layout shouldn't keep you from being able to complete the full ladder. Getting stuck on the full ladder shouldn't keep you from being able to do the Datapath layout, right? Just as long as you're actually laying it out and finding all the, fixing as many errors as possible. In Lab 3, which is what we're going to start covering today, you're going to be going into the Verilog code and actually modifying the finite state machine of the multi-cycle data path that we discussed last lecture. So up to this point, we've discussed the data path, and now we're going to discuss the control. So the control is a finite state machine, which is different than what we were using in single cycle and pipeline. We were using AND gates with inverted inputs when it was a 0 on the opcode. Here, we're actually going to be using these control signals from the instruction to indicate which stages we should be going through in the finite state machine. So the goal of this lecture is to derive the finite state machine, to derive the truth table, and then be able to look at the finite state machine and look at the Verilog code and be able to modify it to add immediate instruction. So I'm going to pick on somebody who, like Christian, I'm going to pick on you. So what is the difference between an I-type instruction and an R-type instruction? I'm picking on somebody who hasn't had my 385 before. Do you recall from last lecture? No? Terrence? Just a lot of heavy squinting. Tyler? No. What is an R-type instruction? All right, so somebody who had my lecture before. Kevin.
The R-type instruction is instructions that use registers. That's the easiest way to.
Right. R-type says for a register. So basically, you're taking two registers, performing some sort of operation in the arithmetic logic unit, and storing in the third register. So I-type instructions are defined as data transfer instructions. So I-type instruction meaning you're getting some sort of immediate value, meaning the last 16 bits of the instruction, sign extending that to 32 bits, and then doing something with that. So in this case, an add-I is what happens if you, let's say you have C code J equals A plus 5. You're going to have the binary value of 5 physically in the instruction. You're going to sign extend it to 32 bits, and then you are going to actually add it in the ALU and store it in the register. So you can't use the R-type finite state machine states because it's actually taking a different set of inputs. So you have to make one stage modified difference, and I'll show you how to do that today. So here's the first step. So this is the instruction fetch. So there are 5 stages in MIPS: instruction fetch, instruction decode, execute, data memory, and write back. So we're going to so in this case we're going to talk about R-type, I-type, branch equivalent, and jump. And the 2 specific I-types we're going to talk about are something called load word and store word. But in your data path that you're going to be doing in this course is going to be load byte because it's an 8-bit data path instead of store word, which would be a 32-bit data path. So all instructions are going to have your initial stage called instruction fetch. So what these circles indicate is we need some sort of value from the program counter. So in this case, instruction or data is going to be 0 because we want the value from the instruction, not data value. Next, we're going to have mem read. We got to read from the memory. So memory read is going to be 1. We're going to have a number of initial set values. So mem write's going to, all of these values are going to be 0 unless they're set to 1. IR write is going to be 1 because we're actually going to be physically updating the instruction register because we want this to indicate it's an instruction. Otherwise, it's going to be 0, meaning we're not going to update it. And this is important because every clock cycle, if you remember from the previous lecture where I had the clocks indicated, the way the register works is it holds the value until the next clock cycle, and then it propagates that value onto the data path. We do not want this to physically propagate an instruction if it's not an actual instruction. So if we're getting some sort of data from the memory, like we're using the memory data register, we want this IR write to be 0, so that way only the most recent copy of the instruction is propagated. Otherwise, we don't want some, we don't want some gibberish. Let's say we had, 4 billion in the value of our memory data for whatever reason, and we just had that here in the instruction, and we just let it go. It would be 0, 0, so it started R-type instruction. But if we're doing a load byte instruction, store byte would even be better for this example. If we were doing a store byte instruction, what would end up occurring is that instead of writing that to the cache hierarchy for the non-volatile memory, we'd just be starting an R-type instruction again. We would have a control hazard, and then we would no longer have the data integrity of the instruction. So this becomes a very important part. Additionally, we're going to start initializing ALU source A here because we're going to increment the program counter, right? So here, I should note the difference. From this particular diagram, here it says 4. That's because in the 32-bit instruction, we'd have to go PC plus 4 to account for 4 bytes. Sorry, 4 bytes, right? In the data path I presented to you last class, this is just 1 because it's just a 1 byte. So I will only want to increment 1. So that's the difference. So, but we are going to add this. So in this stage, if you remember from last lecture, the single cycle data path has multiple adders to be able to add the PC plus 4 and then be able to add branch address. Here in the multi-cycle data path that you're going to be synthesizing, it's only using one ALU, which means it's going to be using the adder multiple times. It's going to use this finite state machine to try to, so the trade-off in a higher control area is it's going to try to reduce the amount of memory and the ALU that's being used, which is also why we set this 0. So we're using PC source set to 0 because we're going to immediately add the value in the ALU and then send it off and just get this next value. So here's the first stage of this finite state machine that we just derived. IRD is 0, mem read and IR write are 1, ALU source A is 0, ALU source B is 0, 1, because we got 0, 1 from here. PC source and ALU op is 0, 0. Why is ALU op 0, 0? R-type instruction, but specifically, because instruction fetch is all instructions, right? But what specifically about ALU op 0, 0 that we presented from last class makes this, but you are correct, Aaron, but
0, 0 means to add, right?
yes, exactly. So ALU 0, 0 means add the PC plus 4 or PC plus 1 in your case and get the next instruction. So all the others, so this is what's initialized. So whenever we start the finite state machine, this is your start state, and then PC write, IR write, all others we don't care. So the next stage is instruction decode. Oh, I should say one thing real quick before we go. So IR write, here it's stated as 1. The way that it works in the data path that you're using, and it's the only purpose for it is the countdown. It is actually a 2-bit control signal, and it'll go 1, 1, 1, 0, 0, 1, 0, 0, and when it hits 0, 0, that's when your instruction decode stage. That's the only purpose for it being a 2-bit value. So instruction decode, what we're doing in this stage is we're taking our 32-bit instruction and we are decoding it using the registers. Now here's the other quirky thing we're doing in instructions. So we're getting the values from here. We're going to be reading from the registers. We're going to be, we have ALU source A is 0, and then ALU source 1 is 1, 1. So it comes from the sign extended immediate value and then has been shifted left by 2. So we're sign extending and then multiplying it by 4. So in the 32 data path, what value is this? This PC plus 4 plus this immediate value. I think that's it. Super. What did we when we sign extended that value and then multiplied it by 4 by shifting left by 2 in the single cycle data path, and we added them together? What did that allow us to calculate? What specific address?
That just wasn't
Not for the memory, no. So we had 2 extra adders in that data path, right? We had one to calculate PC plus 4, and then we had another one to calculate the what address? Not the jump address. You're on the right path, though.
The next instruction.
No, the next instruction is PC plus 4. So if I have to calculate, what were the 3 instructions I could go to? I had to decide between PC plus 4, the jump address, which is what Supervisor just said, and then there's another one, which is the right answer, branch. So this is calculating the branch. So we're taking advantage of this opportunity that the ALU is idle in the first 2 stages of the data path to calculate PC plus 4 and to calculate a potential branch address. And then we're going to be using these control signals to make decide the difference. And this becomes useful because branch only requires 3 cycles. So you have everything you would need before you would need to make your decision. And so this is the second stage. We have made ALU source A 0. We have ALU source B 1, 1 to calculate the branch address. ALU op is 0, 0 to write, and then PC write condition is set to 0. PC write condition. We set that to 0 to prevent overwriting of the PC plus 4. It has, see, because this is an AND gate, so we're not allowing it to go through yet until we make that decision in the next stage. Okay, so does this make sense so far? All right. So in the instruction, so stage 3, I call this instruction independent. So what I mean is it's going to start branching out. So instruction fetch is the same, instruction decode is the same, but once we start getting into load word and store word, R type, branch equivalent, and jump, it becomes different. So in the load word and store word, what we're going to be doing is we're going to be starting to calculate the address that we're going to get from memory or send to memory. So here, what we're going to be doing is we're going to calculate 2 here, which is the sign extended value, and from read data 1. So ALU source A is going to become 1, and ALU source B is going to become 1, 0. And the reason why it's 1, 0 is we're getting the sign extended value. It's not multiplied by 2, because what it's doing, for those of you who haven't had the ES385 with me, is the way the addresses work is like a pointer. The base address of the array is the value that's stored in read data 1. So we get this value from the decode. It tells us where the base pointer of the array is. So think about it in C or C++, right? You have a base pointer of the array, and the offset, if it's A of like 3, the offset is calculated using this value. So 3 would be here, and 1 would be the base pointer of the array. So that's calculated in this third stage in a load of store instruction. And again, it's circled, so I should indicate it. We're also sending it 0, 0 if it's load or store word because we want to add in the ALU. In R type, it's a little different. We're going to send the values from 0, ALU source A is 1, and ALU source B is 0, 0. So we're getting the 2 values from the registers, and we're sending 1, 0 as our ALU op to the control, because we're sending instruction 5, 0 to the ALU control because that's our function value. The function value allows us to differentiate. So 0, 0 in the other load and store word is there in I type is specifically used to add, whereas 1, 0 allows us to differentiate between all of the different R types because the opcode for all R types is 0, all 6 zeros. So that's why this is the way it is. And then for branch equivalent, what we're doing here is we are going to send this value 0, 1, and we send the value from the register and here the register, and what we're going to be doing is we're going to be comparing these values. What we're doing is in the previous stage, now this is where the clocking becomes important. In the previous stage from ALU out, we have calculated the branch address, right? So this is where reuse of the ALU becomes important. We have clocked, we have moved the address that we're going to branch to here. We're then going to move to this to 1. So it's going to be 0, 1 from PC source, right? So now we have our address that we're going to branch to, and at the same time, we're making the decision about whether or not we're going to branch. So if it's equivalent, what that means is if the 2 values are equivalent, we're going to set the 0 bit to 1, and that's going to allow us to branch. At which point PC write condition, as you can see here, is then set to 1. Now it allows us to propagate. So the reason why we have this AND gate is because 2 things have to occur. 1, PC write condition allows us to decide whether or not to branch, and the 0 bit allows us to say whether or not the branching condition has been met. So therefore, PC write condition is going to be 1, PC source is going to be 0, 1, ALU source A is going to be 1, and ALU source B is going to be 0, 0. And so in jump is simple. We have used our concatenate. So we take the 26-bit value from jump, right? So the jump instruction is a 6-bit opcode and the 26-bit value. So what we do is we shift left by 2 in this case. And the reason why that's there is because we're multiplying by 4. And we still have to do that even though it's an 8-bit data path. The 8-bit refers to the width of the registers and the values going into the ALU. We still have a 32-bit instruction. So we still have to shift left by 2. And now, we now have a 28-bit value, right? So what's going to happen is, this says PC 31 to 28. What we're doing is we're taking the 4 most significant bits of the original program counter value, and we're concatenating them onto the jump instruction. So now we have a 32-bit jump address. And by doing that, we now have 1, 0 from our PC source, and this allows us to jump. Yes, Thomas?
Why is this diagram so different from the one in 385?
Because this is from last lecture. Unfortunately, you were sick and you weren't here. We covered a different type of data path called multicycle, and so brief version, and this can help refresh for everybody because this is an important question that Thomas just asked. Single cycle, you have your 5 stages in and all of them have to be the same length, right? In pipelining, you have your 5 stages, but they're broken up, and then, right? But it requires significant overhead. You have to worry about control hazards, data hazards, structural hazards. You have to have your hazard detection unit. You have to have a lot of buffering in between the stages. So we're looking for some sort of compromise between those two. Can we speed it up, but we want to reduce the area overhead?
So is this an out of order instruction?
No. Not quite. What it is doing, though, is let's say load word takes all 5, right? Because it requires a write back stage. So let's say we had a load word that requires all 5. Right? 1, 2, 3, 4, and 5. Now, branch equivalent only takes 3. Well, it requires instruction fetch, instruction decode, and an execution stage because we're using the ALU, and then it can immediately update. So we're not worrying about those last 2. We're using the finite state machine to lop off those last 2 stages. So, and then in addition takes 4 because we don't want to worry about data memory because we're not writing to the data memory. So this would be 4. So the difference here, this would be 5, this would be 5, and this would be 5. So single cycle would be longer than multicycle, but the multicycle has less area overhead than the pipeline. Okay. Does that make sense to everybody? Okay. And so as part of the compromise, we take the 2 adders. We're using the finite state machine to calculate those in the first 2 stages instead of having to add 2 adders to our data path. And we've combined instruction memory and data memory into one memory. And we've used this instruction register to prevent that structural hazard by allowing us to say whether or not it's an instruction or we're getting memory from the data memory.
And what's MDR?
MDR is memory data register. Okay. So here's what we've derived at this point. So we've already derived this stage, and we just went through all of this. So if it's load word or store word, ALU source A, we're getting the value from the register. ALU source B10 is our sign extended value. ALU op 00 indicates write, and PC write condition 0 means we are not jumping yet, or we're not making any PC condition right. Once PC write condition becomes 1, that means we can now make a decision. So what's going to happen, we're going to see that this is actually going to go back to our initial stage, right? So for R type, we have selected both of our registers, ALU ops 1, 0. That allows us to select from our function value, and PC write condition is set to 0 because we don't want to use the branch address. Branching, we set PC write condition to 1 because we do want to use the branch address. We want to have 1 and 0, 0 because for branch, just like we're doing in R type, we want to take those 2 values from the ALU, make some sort of comparison. In this case, we're branching if equal, meaning we're going to the address calculated by the ALU if the values in the 2 registers are equal. Now, where that gets people confused is you want to branch if it's equal. So if you had if I does not equal j, what that means is, and it's handwriting sucks, but whatever. So you'd want to do the value inside the code, right? We want to branch if we don't want to do this code. So it's the opposite of what your actual code is. So branch equivalent would have I does not equal j. And then jump, we set PC source equal to 1, 0, and PC write, because we use that, bless you, PC source gives us our multiplied by 4 and then concatenated jump address. And we set PC write to say we're going to now update that. So here, these values, what we're going to see is the last finite state machine is actually going to come back to our initial start state, but then we're going to have another stage 4 for R type, and then we're going to have stage 4 for, these are going to split up because load word and store word are going to start being different, because now this is where we actually have to do things differently. So for load word, at stage 4, this is where we're actually going to send the value that we've gotten from the arithmetic logic unit to the memory. In this case, it's just memory, and then we're going to get the value from the memory. Okay? So we have to indicate that memory read is going to be 1. We have to indicate the address here. So we have a value from the address. We have our clock signal. So this is where this is coming back from, right? So one of the things that we're using this as they're coming back, we set I or D equal to 1, instruction or data. So in this case, we want data, right? We set memory read as our address. And if you also notice, this is also coming back from our, I'll hit that more importantly when we get to store word. Store word, that's where that becomes important. But here, what we're doing is we're writing back and we're setting mem read equal to 1. And what's going to happen is we're getting the address here. It's going to go into our cache. It's going to get the value that we request, and that's going to put it on the memory data register. That means, of course, IR write has to be set to 0 because we don't want that value that we're getting from memory to be just considered another instruction. So here's where it's different for store word. Store word, what we're doing is, again we're doing the value for the address because we've calculated the address, right? And we're taking mem write because we're writing to the memory. So we need a value that we're writing to the memory. In this case, what's happening is, if you recall, the value that we're going to be writing to the memory comes from read data 2 and goes to the memory. So for load word, what happens is you take the offset from read data 1, you add the result, okay? And the value, and then what's going to happen for store word is you're calculating the ALU, you get the offset, and then you're taking the value from read data 2 and writing to memory. Oh, okay, so I should indicate one other thing for load word. For load word, that second value in the instruction register, which you're not going to really need to know terribly well in this course, that's the register that you're going to write to in stage 5 for load word. But we'll go over that in a little bit. But this is the important point. And here for store word, we take this value, that is our calculated address. This is the value we're going to be actually physically sending to the memory. And for memory write, we have indicated that we are want to write to the memory. And then, obviously, all of the rest of these are going to be 0. And now for R-type instructions, now we have, oh yes, Thomas.
Are we not checking for hazards?
Okay, this is also a very good question. The control signals are what's taking care of the hazards.
Okay.
So by setting value for memory to 0, mem to reg at 0 if we want to do it, as we design the finite state machine, by setting these specific values to 0 and 1, it eliminates those hazards. And to tie into your point a little further, this is how R-type is different. What's going to happen is it's going to set mem read and mem write to 0, so we're not writing to memory. What's going to happen is the mem data register is going to set the value here, and we're going to have our write data. Here we're actually going to set the value to, oh no, this is R-type. Yeah, so R-type, yeah, actually this is a perfect demonstration. So what would happen is it would come out here, right? We'd have some sort of value. and it would want to come here, but since it's 1 and the control signal we've sent is 0, it's not going to write it to the registers. What's going to happen instead is we're going to take the value from the ALU. It's going to come here. We're using the mem to reg control signal, right? Just like we had before in 385. So it's going to set to 0 because we're getting it from the ALU, and that's going to put it in there, and then the register write is going to be set to 1, and the value that we decoded, since it's an R type, we have RS, RT, and RD. RD is the 5-bit value that's waiting on this input of the 1. Then we have our register destination set to 1. It writes to that address. So here's what we've done now. We've completed our branch instruction. We've completed our jump instruction. For R type, we set register destination to 1. That means we want to write to the registers. Memory to reg is 0. That means we're getting the value from the arithmetic logic unit. And the PC write condition is set to 0 because we just simply want to increment our program counter. Again, with store word, memory write is set to 1. I or D is set to 1 because we want the data value coming from there to store to the memory. And then PC write condition is set to 0 because we want to increment the program counter only. We don't want to use the branch address or the jump address. Now, here mem read is 1, IRD is 1, and PC write condition is 0. We probably have noticed that this is not complete yet. And the reason why it's not complete is because we still have to complete the write back stage of the load word. This is, and to answer your question further, Thomas, in order to do branch, we only need 1, 2, 3, and then we start again. To do jump, we need 1, 2, and 3. For R type, we need 1, 2, 3, 4. When we do it, we need for store, we need 1, 2, 3, 4. But for load word, we need 1, 2, 3, 4, and then we're going to have this 5th stage that we're about to derive here. So what the whole purpose of, instead of doing 5 stages for all of these, we've eliminated jump, 2 stages for branch and jump, and we've eliminated 1 for store word and R type. So for load word, what we're going to be doing is we're going to be taking the value from the memory data register, and then we're going to be putting it into the registers. So the memory data register is here, right? So what's going to happen is it's going to come from that memory. We clock it. It's going to go here. Actually, I can zoom in a little bit. This should make it more clear. So it's going to come from the memory data. Memory data register is going to propagate it after the clock signal. The memory or mem to reg is going to be 1 because it's going to come from memory to the register. And then it's going to write the data. And then what's going to happen is register destination is going to be 0. This is an I type, and it's going to say where in the register file we want to write to. So this is the complete finite state machine that that's going to be used in this course. We've derived everything except this last little. Let me scroll up here. We set register destination to 0 because it's an I type instruction, specifically load word. Reg write is equal to 1 because we're writing to the registers, and memory reg is equal to 0. So here's what you're going to be doing in the lab. You're going to be taking this multi-cycle and you're going to modify it to add an add-I instruction. So going back to this data path here, right? So what do you think, actually, it's better off, let's go here. So what do you think is the difference between this finite state machine and if we wanted to add an add-I instruction? Specifically, let me give you a hint. What's the difference between an R-type instruction and an add-I instruction? Well, that's the difference between an add-I and a load word. But you are correct. Yeah, we would not be using this stage, right? No, you're not wrong. What you said is actually correct, and that's important because what you don't want to do is you don't want to create an add-I instruction and have it go to this node because you're then automatically writing back whatever the previous instruction was to your data memory, and then you're getting a control hazard. So what you said is actually a very important point. So what is the difference between an add and an add-I instruction?
Taking an immediate value.
Bingo, right? So is the instruction fetch stage the same? Is the instruction decode stage the same? So execution stage is different, right? So this here is the execution stage. So what's happening is you're just getting a different input value from your R type as opposed to your from your add-I instruction. So what's happening now the write back stage here, not this is data memory, then write back. So the write back stage here for completing R type, is there any difference between that and between add and add-I there? No, because we're taking the value from the ALU and storing it back. So this is the same. So all we want to do is we just want to create another state, node in the finite state machine for this specific. We want it to go through all this. I mean, this when you write this out, because this is a portion of your required assignment. This is the top of guide objective. You'll notice how 0, 1, 2, and 3 are the same, except for this. You will notice that IR write 3, IR write 2, IR write 1, IR write 0. So that's 1, 1, 1, 0, 0, 1, and 0. So it's a countdown. So all of these other values in here are exactly the same. So for 1, 2, and 3, instead of writing all this, just write IR write 2, IR write 1, IR write 0. That should save you some time. I do want you to make your own version of this. I don't want you to screen capture it because it's important for you to actually physically work through, because what you're going to be doing next is you're going to take this finite state machine that you're making and we're going to go into the Verilog code and actually modify it. So that's your lab portion. So here's what we're going to do. What we're going to do is we're going to create another node here. So we have 12 nodes. We're going to call it node 13. And here's what we're going to do. So it would go like this. So let's call it node 13. So this would be 1101, right? And so we have our 3 inputs. So which one is going to be different? We have ALU source A, ALU source B, and ALU op 10. So those 3 values, which ones of those are going to be different? Source B is going to be different. So instead of 0, 0, which one are we getting half?
1, 0.
Yeah, correct. Why is that correct, Supro?
Because we need to choose the third one.
Somebody said 0, 1. 0, 1 is just the 1 increment PC plus 1. So in our node, we're going to have ALU source A is still going to be 1, right? So ALU source, you're going to ALU source A is equal to 1. ALU source B is equal to 1, 0. And what about ALU op?
0, 1.
You're on the right path, but almost. This is an I-type instruction, and we want to add, which should the value be? 0, 0, correct. So we are modifying it to ALU. So what you're going to do is you're going to add this node to your finite state machine, and then the next thing you're going to do is you're going to have your node that you modified, and then you're going to have this come back to 10. Right? And so here are the actual values that you're going to put in node 13. You're going to put ALU source A is equal to 1. You're going to put ALU source B, the ALU source B is equal to 1, 0, and ALU op is going to equal to 0, 0. And then add node 1, 1, 0, 1, your FSM in the lab report. So my recommendation, handwrite it out, or if you're the type of person who feels more comfortable using a text editor, do that. Whatever you feel will be done faster. Don't rewrite all these. Just write ALU, write 2, write 1, and write 0 for those 3 nodes. That is how it's coded in there, so I'm going to insist that you at least add those. And then just add the node. And then for those of you who have the questions, this is a very common question, what's actually physically going on? So here's what's actually going on in this truth table, which is to be included in your report. So here, these are actually the initialized zeros. So it's actually a 4-bit value. So it's 1, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. So that's your IR write decrement. So those are the first 3 stages. So these node values correspond to these numbers here, right? So 0, 1, 2, and 3. So node 4 is your instruction decode stage, which we've calculated. Let me zoom in a little more. PC write is 0. The key details is ALU op is going to be 0, 0 because we're going to be adding the value from 1, 1, which is our sign extended, multiplied by 4, because now we are calculating our branch address. So that's the important details. We have a lot of these values where we don't care what the register values are, and the reason why they don't care is we want to reduce area overhead. Now that you're familiar with synthesis algorithms, if you have a 0 or a 1, you have to do some sort of either gray encoding or K-maps or quantum Mikulski reduction. If you have a don't care, it reduces your area overhead, right? So a lot of these are going to be don't care values. So what I'm going to do for those of you who are, I'm going to zoom in and slowly scroll left for those of you who are watching this on the video later. So I know I get complaints about I'll move back and forth and people are trying to quickly press pause. So this is what I'm trying to take your concerns into account. So 1011, we have these values we're adding. So we have one, we're adding these together. So this is some sort of I-type instruction. In this case, it's going to be your load word, load word or store word calculation. Here, we're having branch and jump. So we have a bunch of don't care values here. Right, we have PC write condition set. Once we get to stage 7 and 8, let me scroll over here because I wanted you to see. This is stage 13. This is the one that you guys just designed. So the stage, so stage 12 is the last value from that load word, and stage 11. So you notice that here, let's find the. Yeah, so here we go. It's going to be this one. Sorry. This is the last stage of your R-type instruction here. And this is not the last stage, but this is the stage where you're branching off. So what we have is we have our instruction decode, and then it's going to branch off where we had our R-type, which is 9, and then we have our I-type, which is 13. And then they both go to 10, right? So those are both going to go to this one. So you notice how these are the same, except, right? That's where it changes. So that's the difference between R-type and I-type. And so, does anybody have any questions about that before I move on? All right. So, here's what is actually going on here. So you have your control logic, right? So if you recall, when you have your finite state machine, you have some sort of input set, you have some sort of output set, and you have your current state registers, right? So the state of the register plus the input contributes to the output. So what type of state machine is this? Is it a Mealy or a Moore machine? If it has the inputs and the state register values contribute to the output. I'm sorry, what did you say? Peter? It is in fact a Mealy machine. I thought somebody said Moore machine. My apologies. That was the correct answer. So what's happening is, at every state, you have the instruction value, and you're only overwriting this when the IR write becomes 1. Otherwise, it's holding that same initial value, right? So if it's an R-type instruction, what's going to happen is it's going to go to 0, 1, 2, 3, 4, and then a finite state machine, the next state register is going to update the values Right? So it's going to make that decision, go, all right, go to 9, then go to 10, and it's going to update these outputs accordingly. So that physical implementation that you saw is modified by the state registers. So you notice it has a little system clock in there, as I mentioned last class, that can cause a little bit of a nuisance in job interviews. You forget to mention that. And so that's your output state. So that's combining everything together. This goes to the data path that we discussed last class. And this opcode is your 31 to 26, which comes from your IR write value, or from your IR register, from IR write, to propagate on there. So that's how everything's implemented in the multi-cycle data path. Okay. So what we're going to do next is we're actually going to, this is actual controller V. The value that you had, it's what I did is I did controller_solution.v. It's because you would need cadence tools to be able to properly synthesize it from what you have. So I've cut some work out of the lab for you. But what we're going to be doing is we're going to be going over this because now we've done some VHDL. We have our initial module, and so we're setting all of our control signals. We have our opcodes. We have our 0-bit, right? So now we have all of our control signals on our output, plus we have our clock signals and our reset signal. So as you guys now know, you initialize all of your inputs. So you don't have to modify anything here. Where you start to have to modify is your multi-cycle state machine definitions. So these are the current states that you have. So as you can see, these values here are pertaining to your truth table. So this is why doing the truth table is important other than just doing busy work. You should know what the values are. So if we went through 1100 and we initialized our defined state as 1101, what do we need to do here in order to be able to, this is the first place you're going to modify the code. What do you need to do? Let me zoom in a little bit so you can be more clear. So this is your first modification is going to occur. So we had our states in our FSM that went up through 12, right? So we went through 0 through 12, and we added 1101, right? Yeah, so how would you do that? What would you say you want to do here? So look at the code and write an actual line of code. Parameter add I, and you could say parameter add I. I would add, just for the time being, right? Add I x equals 4 B1101 semicolon. Right? And the reason I'm just going to say add I is because I want you to add. The next thing you're going to do is you're going to add the instruction opcode. So from the instruction opcode from 8, from section 8, which is where I presented it, what's the specific instruction opcode for add I?
Was it 10?
No, it's not. No, this is jump is 10.
Oh, okay.
It's actually 1000. I just happen to remember that off the top of my head. Or 001, because you don't get confused with store byte. But you would just add parameter add I here equals 6 B001000 and refer to that in your section 8. So that's why I included that table in the TGOs, because you're going to refer to it while writing your code. So here you have all of the internal signals, which you do not have to modify because the internal signals remain the same. So here we have what this state register is you're using the clock to use the master and slave latches to be able to propagate here. If you recall, this is actually using a 2-phase clock. to propagate the signal. You guys learn how to do that in CMOS. Your tool will synthesize it down to what you learned in section 5. Yes, Terrence? Oh, no, I was scratching your head. Okay. So next state logic. This is where your next modification is going to be. You're going to start at 0, then you go to fetch 1. So here it is. Next state, 2 goes to fetch 1. Fetch 1 goes to fetch 2. Fetch 2 goes to fetch 3. Fetch 3 goes to fetch 4. That's just your IR right counting down. And then fetch 4 is going to go to decode because instruction decode is required for every instruction. So then you have your phi 1 and phi 2 occur. And then from your decode, you're going to use this 6-bit opcode value to make your next decision. Here, you're going to load byte. So mem adder was the name of that node in the finite state machine. Here for R type EX, that was that node for R type. BEQ next state 2 is BEQX. Jump is JEX. And default is going back just to the fetch 1. So what would you need to do here in order to modify this code in order to add an Addi instruction? I'll zoom in a little bit. So first of all, what was the name of our Addi node that we created? Addi X, right? So, and what was the name of the actual Addi instruction? Addi. So just follow the pattern here and come up with your next Addi node. Okay, so hold on. Before you step at your Addi colon.
Next state underscore S2.
Mm-hmm.
Loaded with
Bingo. There you go. That's the right
semicolon.
Semicolon. Yeah. Okay, so now memory address goes to load byte and store byte like we expected. And then here you're actually doing the last stage of the load word. Doing store word, we're going back to fetch 1. R type REX here. The next state is R type, let me write this out so you know. So that's where we're going to be writing back to the registers. And then branch equivalence ended and jump is ended. So what would we need to do here to modify our Addi instruction? Yeah, because it's going right back to the node. So let's write the code again. Addi X colon.
Next state colon's head.
Yep.
2 is loaded with R type RWR.
Bingo. Exactly right. There you go.
No problem.
And then this is always the initial state. So this is the last thing you need to do, right? One last thing. So here you're actually defining the signals when you get to that node. So the last thing you need to do is what? And add IX. So what's the difference between add IX and, so we have add IX begin, and then ALU source A is still 1, right? What was ALU? So what was ALU source B? 1, 0. So ALU source B1 is going to be 1. ALU source B0 is still going to be 0. And so what was the ALU output we derived? 0, 0. So ALU op 1 is going to be 0, and ALU op 0 is going to be 0. So go through and write and tell me what your code is going to be. I know I just described it, but I want you guys to actually say it out loud.
Add X semicolon.
Yep, exactly right.
Long colon. Begin. ALU source A loaded with 1.
Okay, someone else besides Coleman, so Coleman, this is the first step.
All right, you're good.
ALU source
Yeah, okay.
1 is loaded with 1.
Okay, you pick the next person.
ALU
Oh, no, you want to step ahead of me. So ALU source B1 is equal to 1, so what's ALU source B0?
0.
All right, pick the next person. Someone hasn't gone yet.
LU up 1 is loaded with 0.
Mm-hmm.
Let's get Kevin going.
All right.
ALU op 0 is loaded with 0.
Okay.
And
And very good. Okay, so this is where I want. Let's just end here today. In the next lecture, we're going to start going into the physical design flow. What's actually happening? So now you have your code. You've gone through everything. You've designed a data path. You've designed a controller. You've written everything in VHDL. You've come up with all your inputs, and then the design tool does something, and that's what we're going to start learning about next lecture. Okay. So, does anybody have any questions before I dismiss class? All right. Please have a rough draft of your presentations due on Thursday. Okay.